Hello students, today our topic is real numbers CBSE syllabus 10th class. I will cover this chapter in 20 minutes. You may surprise, I am very sure you will learn all the topics in the real numbers. So what you learn in this class is some natural numbers, whole numbers, integers, rational numbers, irrational numbers. Finally, the real numbers you will come to know. Then we will see what is the fundamental theorem of arithmetic and some example problems. Then we will find LCM and HCF by using the prime factorization method and some example problems. Finally, we will have some of the proofs, irrational number proofs, that is root 2 is irrational number, root 5 is irrational number, all this you will learn. So that you will cover entire chapter, okay? So let's start. Natural numbers are counting numbers, so that you can count with your fingers like 1, 2, 3, 4, 5, etc. So called the natural numbers. So it does not have any fractions numbers and does not have any zero and negative numbers like that. Okay, so this is denoted with letter n. When you come to whole number, that is entire natural number. Addition to that is a zero. If we add it, you will get the whole numbers. So we are just adding the zero to the natural numbers. We will get the whole numbers. Okay. What about the integers? Integers are whole numbers plus negative numbers. Okay. So it has 1, 2, 3, 4 positive numbers and -1, -2, -3 negative numbers, and it includes 0 also. So it does not have any of fractions. This is denoted with letter C. Now we will see rational numbers. So rational number is denoted with letter Q. Why do we are defining with letter Q? I will explain a little bit later. Let's see first what is the rational numbers. If you write any number in the form of P by Q format, that numbers are called the rational numbers. So here P, Q are the all integers. Okay. So integers, right? 0, positive numbers and negative numbers. Right. Here Q is not equal to 0. If Q is 0, right, we cannot define the number. That's why Q is not equal to 0 here. So here Z is the integers numbers I said, right? Okay, now, so some of the examples, if you see, it's 2 by 3, 5 by 7, 11 by 9, etc. So all these numbers are rational numbers. Since we are written in the P by Q format, here P and Q are the integers, right? So I'll give you an example. So can you tell me whether 15 number is the rational number or not? Yes, it's a rational number. So if any number can be written like denominator with 1, right? So it's a 15 by 1. So it's also P by Q format. So all integers, whole numbers, or whatever you take, right? All are rational numbers, right? So why you are denoting with the letter Q, right? It's a quotient, right? When you divide with one number to another number, what you get? You'll get the quotient, right? That's why this is denoted with letter Q. Oh, okay. So if you take a rectangle triangle, right? And we are taking the side length of 1 and 1. Okay. So what you get the hypotenuse? If you use the Pythagoras theorem, you will get 1 square plus 1 square and square root, right? So you will get the hypotenuse the square root. Okay. So when you trying to find the square root to value in decimal places, then we get something like this in the calculator. If you type in the calculator square root of 2, you get like 1.414213 and etc. And it's keep getting these so many numbers, okay? So it won't terminate, okay? So now I will define something like this, irrational numbers. Irrational number consists of the non-terminating and non-reoccurring decimals, okay? Those are called the irrational numbers. Means the decimals are never terminating, okay? It keep coming and keep going, okay? And non-reoccurring, repetition also will not be there. We don't know what number will get the next. So here the numbers won't repeat and it won't terminate. It keep coming, okay? Those are called the irrational number, and these numbers cannot be written in the form of P by Q, okay? So these numbers we never cannot write in the P by Q format. So here P and Q are the integers, right? So that format we cannot write here, okay? So I'll give you an example now. Let's check. This is the rational number or irrational number. If you cleanly observe this, 142857, right? 142857. The numbers are repeating here, okay? This is not the irrational number. It is a rational number because numbers are repeating. Okay, so it is 22 by 7 actually. Okay, 22 by 7 is rational number, not the irrational. Why? We already written in P by Q format. Here P is 22 and Q is 7, right? Now, so some of the examples, right? Root 2, root 3, root 5, pi, e, all are irrational numbers. Okay, so this is later denoted with Q dash. What about the Q? Q means rational numbers. Q dash means which is not, usually dash will put which is not, or is opposite to that, right? So real numbers are, entire rational numbers and irrational numbers are called the real numbers. Okay, so the really existing numbers these are. Okay, that's why they're called the real numbers. Okay, that means we can put these numbers in the scale bar. Okay, if a scale bar, if you take it like positive numbers, negative numbers, 0, and all these rational numbers and irrational numbers, you can keep it on the scale bar. Okay, that's why we are calling real numbers. Okay, so Q dash is defining something like R by Q. That means entire real numbers, if you remove the rational numbers, we'll get irrational numbers. That's why it's denoting something like R by Q or Q dash. Okay, now we will know about the real numbers, right? Okay, now we will see the fundamental theorem of the arithmetic. Before learning definition of fundamental theorem of arithmetic, we need to learn about these three terms. One is the factors, prime numbers, and composite numbers. First, we will see what is the factors. It's a completely divisible numbers are called the factors for that number. For example, 5. What are the numbers will be divisible completely to 5? We know that 1 5s are 5, right? So 1 is a factor for the 5, right? The another one is 5 1s are 5, right? So 5 is the another factor for the 5. Okay, so if you write the factors for the 5, you can write 1 is the one factor and 5 is another factor. Is any other number is divisible with 5? No, right? That's why we have the two factors. 1, 5 are the factors for the 5. Okay, so if you take another number, something like that, 10. Okay, so what are the factors for the 10? So 1 10s are 10, 2 5s are 10, 5 2s are 10, and 10 1s are 10. So any other number will be divisible to the 10? No, right? So for the factors for the 10 is 1, 2, 5, 10. Okay, so okay, now come to the prime numbers. For any number, if you have the only two factors, that number and 1, only the factors, that numbers are called the prime numbers. For example, here 5 if you take, right, that number means 5 is the factor and 1 is the factor. Only having the factors 1 and that number. Okay, if that number are the factors, those are called the prime numbers. Now if you see the example of the prime numbers 2, okay, that number and 1 is the factors, right? So 2 is the prime number, 3 is the prime number, 5 is the prime number, 7 is the prime number, 11 is the prime number. So here, so for the factors for the 2, if you see 1 and 2, right? So here 1 and 3, here 1 and 5, here 1 and 7, so 1 and 11. So no other factors for these numbers. So those are called prime numbers. What about the composite numbers? Composite number means if you have any one extra factor than that number and 1, okay, those numbers are called the composite number. For example, 10, okay, so it has the factors 1, 2, 5, 10, right? So in your 1, 10, other than the 1 and 10, it has the 2 as a factor, 5 as a factor. Then 10 we are calling the composite number. 4 we are calling the composite number. Since it has the, instead of 1, 4, it has the 2 also, right? 2 into 2 also 4, right? So any one extra factor it has, that those numbers are called the composite numbers. Now we will see definition of the fundamental theorem of the arithmetic. Okay, so every composite number can be expressed in the product of the prime numbers. So any composite number can be expressed in the form of product of the prime numbers. This factorization is unique, okay, apart from the order which the prime factor occurs. Okay, so it's easy to understand, right? So any composite number, for example, 10 can be written like 2 into 5, right? So here 2 is the prime number and 5 is the prime number. So any composite number can be written product of the prime numbers, and we can write orders like 5 into 2 or 2 into 5, it does not matter. And this is unique, okay? So we cannot write any other two prime factor multiplications. If we written 10, always you can write only 2 into 5 only. You cannot write like something like other prime multiplications. Okay, only you can write these two prime multiplications. Okay, so that means it's a unique. Okay, but order it can be changed. That's what the statement is. So every composite number can be expressed as a product of the prime numbers. Okay, and this factorization is unique apart from the order in which the prime factors occurs. Okay, it's a very clear definition and a clear, simple definition. So now we will see some of the composite numbers. Okay, we will express into the product of the prime numbers. Now we will see for the 156. So if you see 156, we know that it's very clearly divisible with 2, right? Because end number is the even number. So we will be dividing 156 with the 2 number. Okay, then what we get? 2 7s are 14 and 2 8s are 16. So we'll get the 78. So that 156 can be written like 2 into 78, right? So 2 we cannot simplify it further. So we'll simplify further the 78. Okay. So 78 is also even number at the end, right? So it again divisible with 2, right? So this number can be written like 2 into 39. Okay. So if you see 39, 3 and 9, sum of these two numbers is, if you take 12, right? 9 plus 3, 12. 12 is divisible with a 3. So that the entire number also will be divisible with a 3. Okay. So this number can be written like 3 into 13. 13 is a prime number, so that it cannot be divisible by any other number. So 156 can be written like 2 into 3 into 13, right? So we have written product of the prime numbers. So here 2 into 2 can be also written like 2 square into 3 into 13. Okay. So finally we written the number, the composite number 156 into the product of the prime numbers. This is what the arithmetic theorem says. Okay. So now we'll see the example for the 1000. So 1000 can be simply again split between 10 into 10, right? So if you find for the one prime factors, then just you can double because it's the same, right? So that's the reason simply you can do it like 10 into 10. 10 can be written like 2 into 5, right? So if directly you can write now for the 1000. That is, it's a 2 square and 5 square. Okay? Because it has the 2 tens. You need not to do it again for this 10, right? Now we'll see for 5005. So it is divisible with 5. So that we can write 5 into 1001. 1001 is divisible with 7, right? So 7 into 143. 143 is divisible with 11 into 13. Okay. So that 5005 can be written like 5 into 7 into 11 into 13. Okay. So any number can be expressed as a product of the prime numbers. This is what the arithmetic theorem says. Now we'll find LCM and HCF using the prime factorization method. You know what the LCM, right? It's the least common multiplier and highest common factor. Let's see. First we'll take these two numbers and we'll write each number in the prime factorization with product of the prime numbers, right? Okay, first we'll take 336. This can be written like, if we divide 3 with, right, it is 112 we'll get. So we know that this number will be divisible with 2. So we'll do it again with 2. Okay. So we'll get like 2 into 56, again 2. So it's 28, again with 2. We'll get 14, again with 2, we'll get 7, okay? So finally, the 336 number can be written like 2 power 4. We have the 4 2s, right? So 2 power 4 into 3 into 7, right? Similarly, 54 also will write the same way. So 2 into 27. So 27, we know clearly it's a 3 into 3 into 3, right? 3 cube. So simply written so very quickly. So it's 3 cube. So 54 can be written like 2 into 3 cube, okay? So first we will take the highest common factor. So highest common factor, just see what is there common between these two numbers. If you check it here, 2 power 4 is there here, but 2 is here. If you take the common in these two numbers, only 1, 2 we can take it, right? We cannot take more than that 1, 2 out of these two. So that 1 has the common factor into, next if you see here 3 here 3 cube. So common in these two is only 1, 3, right? So 1, 3 is the common. Anyhow, 7 is not here. So that only common prime numbers are here. 2 is the one number and another is the 3 is the another number. So that common factor will become like 2 into 3, 6. So the highest common factor can be found easily with this method like this. Okay. So I will explain you how do you do LCM exactly. Okay. So just take the 2 here first. Okay. Here also 2 is there. 2 power 4, 2, which is the maximum. 2 power 4 is the maximum. So put that highest number, like 2 power 4 here. Here 3 is there, here 3 cube is there. Which is the max? 3 cube is the max, right? Put the 3 cube here, okay? Here 7, here no 7. So that we need to put that 7 corresponding, okay? If you multiply all these numbers, you will get the least common multiplier like 3024. So given that HCF of these two numbers is 9 and LCM of these two numbers, we need to find, okay? So what I said, product of the two numbers equal to HCF into LCM, I said, right? So here HCF is given like a 9. We need to find the LCM, okay? So HCF, we know 9, and LCM we need to find. And the product of the two numbers means 306 into 657, okay? So if we simplify this, we will get the LCM 22,338. So this kind of product method will not work for the three numbers. It will only work for the two numbers, okay? So now we'll see this 510 and 92. Okay, we'll find the LCM and HCF. Now first we will do as is, right? 510 we will write in the multiple of prime factorization methods, okay? So I'm just quickly showing, okay? 510 can be written like 2 into 3 into 5 into 17. Order does not matter, okay? So similarly we do for the 92 also, okay? So when you do for the 92 can be written like 2 into 2 into 23. So 2 into 2 means 2 square into 23. First we will find the HCF. So only 1 is the common, here 2 square. So 2 only is the common factor in this 2, okay? So that common factor will become only 2, right? So for finding the LCM, 2 if you take here 2 is there and here 2 square is there, which is the maximum 2 square. Here 3 is there, here no 3. So we'll put 1 3. Here 5 is there, here no 5. We'll put 1 5. Here 17 is there, here no 17. We'll put the 1 17 here. Here 23 is there, here no 23. We'll put 123. If you multiply all this, we'll get the LCM. So this is how we will do the LCM and HCF using the prime factorization method. So now finally we come to the last topic in our chapter, that is we need to prove the root 2 is a rational number, okay? Before we are proving this root 2 is a rational number, we need to know one theorem, okay? That is theorem 1.2, okay? What it says, right? If P is the prime number, P divides A square, then P must divide with A, okay? It's a very simple theorem, we can prove it, okay? So what it is saying, right? If A square is our number, okay, that is dividing P. P is the one prime number, okay? Then it is saying that P also divide with A, okay? Number. For example, let's take A is the one number, okay? So what I said, any number can be written like product of the prime numbers, right? So I'm writing now product of the prime numbers like P1 into P2 into P3, okay, into so on until Pn I have written, okay. So these are all the product of the different prime numbers. I have written A number. So what about the A square then? We need to multiply this one twice, right? Then what we get here in the A square? We get like P1 square into P2 square, right? Into P3 square, okay, and so on, Pn square, okay. So let's take any prime number. For example, I'm taking P3 as the one prime number, right? Any prime number that is dividing with A square, right? So now A square is divisible with P3, okay, because it's twice is divisible. Then we can know that clearly the same P3 is also there with A prime factorization. So that P3 also divides A also, okay. That is what this theorem says. Simply we can prove it, okay. That is what the proof is. It's very simple proof. Now we are ready to prove the root 2 is a rational number, okay. First, let's take root 2 is rational number, okay. Let's take, this is what the contrary statement, okay. Because we need to prove the root 2 is a rational number, we have taken root 2 as rational number, okay. So if you assume like this, we will come up with some wrong statement or deadly wrong conclusion we will get. From that, we will say that root 2 is not rational number and we are proving the root 2 is a rational number, okay. First, we will take the root 2 is rational number. What I said, any rational number can be written like in P by Q format, right? Let's write in the P by Q format. P, Q, I'm just putting the letters, right? So it may be anything like that, R by S or P by Q. So let's take the R by S. Of course, here S is not equal to 0, obviously, because if S is equal to 0, this number cannot be defined. So I have written this number into R by S. Now, if you take any divisible of the two numbers, some of the factors get cancelled, right? For example, 2 by 4 is there. Right? Some of the numbers will get cancelled. Here 2 1s are 1, 2 2s are 1, 2, okay. So this also can be written like 2, okay. Now I'm cancelling all the common factors in the R and S. I'm rewriting this one with A by B, okay. So A by B here are the co-primes. Co-primes means, so for the A and B, there is no common factors. So that we cannot cancel out on one. Okay, we cannot cancel out. So A and B are no common factors. Clear? So root 2 now written like A by B. Okay. So now if we cross multiply A equal to, we can written like B into root 2. Okay. So if we are squaring both sides of the equation, we will have like A square equal to B square into 2. So now we are clearly now A square we have written in the 2 into B square, right? So for A square, 2 is the one factor, B square is the one factor, right? That means A square is divisible with 2. Theorem 1.2 is saying that, then it divide with 2 also, right? So A square divide with 2 means A also divide with 2, okay? So A is divisible with 2, okay? This is a statement number 1. Now what you do, right? So A is divisible with 2, right? That means A you can written like some other number like 2 into C, right? Because A is divisible with 2, clearly. So that I am writing A is equal to 2 into some other integer C. C is the another integer, okay? Now we will replace A into with 2 and C here, okay? So if we do that, in this equation, 2C whole square equal to 2 into B square, okay? So that we will already get 4C square equal to 2 into B square. If we simplify this, 2C square equal to B square we will get, right? Now, if we see clearly this one, right? B square divisible with 2, because B square we have written 2 into something, right? That means B square is divisible by 2. If B square is divisible by 2, okay, B also divisible by 2, right? That's what the theorem says. So from these two, this is the second statement. From these two statements, A comma B have the common factor of the 2, okay? What we assume, A comma B does not have any common factors, we assume, right? But we got the common factor for the A comma B is 2, okay? That is the contrary statement which we assumed. So this is erased. This controversy statement is erased because we assumed the root 2 is a rational number. So that root 2 is a rational number, okay? If you want to go by step, I'll clearly explain from here. You can see here. So let's assume root 2 is contrary statement we are taking. That is root 2 is a rational number. If root 2 is rational number, that can be written like R by S format, right? So if we cancel out the common terms in the R comma S, and we written like Q by A by B co-prime numbers. Here A comma B are the co-primes. There is no common factors for the A comma B. So if we simplify this, A equal to B into root 2, and if we are squaring both sides, we will get like 2B square is equal to A square. That means 2 divides A square. The theorem says that 2 divides A, right? If 2 divides A square, 2 also divides A, okay? Similarly, 2 divides A, right? That means A can be written like another, because it's divided with 2. So 2 into something it can be written. That something is I'm taking is here C. So A equal to 2C. If we substitute in this equation, we'll get B square is equal to 2C square. That means B square divides with 2. Theorem says that 2 divides B. That means A comma B have the at least 2 as the one common factor. Okay. This contradicts is happening because we assume the root 2 is a rational number. So root 2 is a rational number. Sometimes you'll ask to prove that 5 plus root 2 is a rational number and root 3 is a rational number. We can say that very clearly, one irrational number and rational number, right? Finally, we'll get the irrational number only. Okay, that we can prove very easily. Let's take 5 plus root 2 is a, as we assume, right? 5 plus root 2 is a, first we take the contrary statement, that is, we will take it as a rational number. So that we can write in the format of P by Q format, okay? If we simplify this one, root 2 equal to P by Q minus 5, right? So if you take here P minus 5Q by Q, okay? So right side number is the, again, rational number. Clearly it's showing the rational number. So the P is the rational number, Q is the rational number. So, sorry, P is the integer, Q is the integer. So that P minus 5, Q by Q also a rational number, right? So, but left side root 2 is the irrational number. So this already we proved. So that we need to prove separately root 2 is a rational number. So that we can say that one irrational number cannot be equal to rational number. So that 5 plus root 2 is irrational number. That way you need to prove it. Okay. Similarly, 5 root 3 also you need to do that way. Okay. So this is the end of the class. Okay. If you have any questions, you write in the comment section. And if you like the video, press the like button and share with your friends. Thank you.